Good morning, distinguished colleagues and guests. It's December 22nd, 2021, 11 a.m. Moscow time. We're beginning the panel session for the defense of the thesis by Mikhail Dobrynin. The thesis is submitted for the academic degree of Candidate of Sciences in Chemistry. The specialization is 147, macromolecular compounds. The topic of the thesis is complexes of platinum metals as cross-linking catalysts and luminescent polysiloxanes fillers. Under the order issued by the Academic Secretary of St. Petersburg State University as of October 6, 2021, number 9526/1, I, Ivan Zorin, Doctor of Sciences in Chemistry, Associate Professor and Acting Head of the Department of Macromolecular Compounds Chemistry of St. Petersburg State University of the Institute of Chemistry, was appointed the Chairman of the Board. The order also approved the members of the Board, namely Nadezhda Bokoch, Doctor of Sciences in Chemistry, Professor of the Department of Physical Organic Chemistry of the Institute of Chemistry of St. Petersburg State University. Alexander Yakimansky, Doctor of Sciences in Chemistry, Director of the Institute of Macromolecular Compounds of the Russian Academy of Sciences. Mikhail Goifman, Doctor of Sciences in Chemistry, leading researcher at the Laboratory of Polymeric Nanomaterials and Composites for Optic Media, Institute of Macromolecular Compounds of the Russian Academy of Sciences. The following member of the board is working remotely today. Sergei Kostyuk, Doctor of Sciences in Chemistry, Professor, Head of the Department of Macromolecular Compounds of the Belarus State University. Sergei, do you see and hear us? Yes, I do. And I see you quite well. Okay, thank you. And our candidate for the degree is Mikhail Dobrynin. And we also have Regina Islamova, a Doctor of Sciences in Chemistry, Associate Professor, Professor of the Department of Macromolecular Compounds of the Institute of Chemistry of St. Petersburg State University. She is the thesis supervisor. I would like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into English. Currently, we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions and comments to Mr. Dobrynin online, questions regarding the thesis or scientific discussion. And thus they can participate in the discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the presentation and to the content of the thesis, and do not forget to give your name and position if you submit a question. Questions that have nothing to do with the scientific discussion or the dissertation text and anonymous questions will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts of St. Petersburg State University, the session of the Dissertation Board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people, and our dissertation board consists of 5 people. Everyone is with us today, including one member of the board who is working remotely. And we have a multimedia connection with him, therefore we have the quorum. And I ask the representative of the Department of Dissertation Board Support to fill out the attendance list. Well then, our session should not last more than 2 hours, and the agenda is as follows. First, we're going to listen to the chairman's presentation about the documents submitted by the candidates for the degree and their conformity with the requirements, followed by chairman's replies to questions, if any. 5 minutes will be given to that. And then a short presentation by the candidate for the degree, providing an overview on findings of the research, 15 minutes for that. Then questions to the candidate regarding the presentation, 10 minutes per question. Then the candidate's replies to the questions, 5 minutes for all the questions. Then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions to the candidate for the degree. 10 minutes each. Then the chairman's report on the thesis, 10 minutes for that as well. Then the candidate's comments about the report on the thesis and replies to the questions, 20 minutes for all. Then we're going to have an open discussion, speeches by those present at the defense with a brief presentation of their positions or questions or suggestions to the candidate on the topic of the research. 2 minutes per speaker. And at that, I kindly ask you to fill out the registration form and do not forget to state your full name, academic rank, position, and the place of work. Then the chairman will ask the questions submitted during the broadcast via our website. And I would like to draw your attention to the fact that all the written questions that will take more than 2 minutes to read out will not be voiced. Then the candidates replies to the questions, 2 minutes each. Then presentation of the candidate's thesis supervisor, 3 minutes for that. Then we may have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results is not broadcast. Then we're going to have an open balloting procedure where then we will count the votes and record the results in the protocol. Afterwards, we're going to make a decision on whether to confer the academic degree or not. And finally, we're going to the candidate's closing speech, and 2 minutes will be given for that. Distinguished colleagues, are there any questions or objections about this agenda? So no questions or objections, and as there are none, I will start my presentation. So don't forget to turn off the sound on your mobile phones, and let's begin. So can I start then? Oh no, I beg your pardon. I beg your pardon. Now it's my presentation. So our candidate for the degree is Mikhail Dobrynin. This is by Mr. Dobrynin for the academic degree of Candidate of Sciences in Chemistry. The specialization is 147, macromolecular compounds. Is titled Complexes of Platinum Metals at Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers. A thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued September 21st, 2021, number 9006/1. Mikhail Dobrynin has prepared his thesis at St. Petersburg State University as a postgraduate student, and Regina Islamova, Doctor of Sciences in Chemistry, Associate Professor, Professor of the Department of Micromolecular Compounds of St. Petersburg State University, is the thesis supervisor. 5 published works describe the research findings. There are no publications in peer-reviewed journals recommended by the Ministry of Education and Science of the Russian Federation, and 3 papers are published in journals indexed in Web of Science and Scopus. As far as I'm informed, all the submitted documents comply with the requirements and are found in the certification file of the candidate for the degree, and the curator of the defense, the member of the Department of Dissertation Board Support, has all the copies of these documents. And before I give the floor to our candidate for the degree, I would like to ask the members of the board, distinguished members of the board, do you have any general questions to the candidate for the degree, and is there a need to consider the whole list of documents submitted by the candidate? No questions, okay. So finally, I would like to give the floor to Mikhail Dobrynin, our candidate for the degree. So please, Mikhail, you have the floor. The topic of my thesis is complexes of platinum metals as cross-linking catalysts and luminescent polysiloxanes fillers. Catalytic hydrosylation is a key reaction to obtain such compounds. The reactions are different because we have the attachment of hydrate to the compound that contains double or triple chain of hydrogen, and these are catalytic reactions, and as catalysts we use metal compounds, and most efficient catalysts are compounds of a platinum group and iridium group compounds. And one of the most practical implementations is hydrosylation in polymeric chemistry that allows us to obtain silicon rubbers. During the reaction, we have the reaction between polysiloxanes and we have silicon rubber as a result. Such rubbers are quite in demand because they are thermally stable. They don't change characteristics at different temperatures. They have insulation characteristics, low temperature of glass formation transition, and thus they are actively used in all the spheres, including robotics, biomedicine, and engineering. Most frequently, for cross-linking of polysiloxanes, we use Karsid catalyst, the complex of the one that is present on the slide. But due to its high activity at room temperature and at heating, during use we need to add up inhibitors. As inhibitors, we mostly use malates and fumarates, but we can also use other non-saturated compounds like spirits, phosphines, and sulfoxanes. And Karsid catalyst application without inhibitor leads to low-quality rubber with different cracks and opacities, and thus it reduces the quality, it compromises the quality of the material. And in literature, we've already seen the attempts to stay away from Karsid, catalyst, and inhibitor combination. Thus, we know a range of complexes based on platinum, iridium, and rhodium. But in the majority of cases, scientists did not study the impact of these complexes that were used as catalysts on the characteristics of silicon rubbers obtained. And no attempts were made to use these catalysts for targeted change of characteristics. One of such characteristics is luminescence. In literature, we know three most frequent ways to obtain luminescent silicon rubbers. The first way is the introduction of luminescent fillers into the silicon compound. The second way is to use functionalized polysiloxanes and administration of metal, during which we get the following complex. And the third option is to use prepared polysiloxanes for cross-linking. The first way is quite simple, and at that, as during the procedure we use catalyst, it's not rational to simultaneously administer filler and catalyst if we can unite them, both characteristics, into one compound. Thus, the goal of this work was to search for complexes of platinum group metals that would allow us to get luminescent polysiloxanes. And the second goal was to search for new metals that would allow us to provide an alternative to Karsid catalyst and to study the impact of their characteristics on the characteristics of rubber materials. And as a result, we resolved the following goals. The first goal was to obtain silicon rubbers using phenylpyridine complexes of third iridium and the optimization of conditions for cross-linking. Second goal was to obtain silicon rubbers using phenylpyridine complexes of platinum-2 and optimization of conditions. Then third goal was to obtain silicon rubbers based on neutral complexes of platinum-2 and the study of impact of ligand environment on catalytic activities and the comparison of catalytic activities with commercially accessible carside catalyst. Fourth goal was to obtain silicon rubbers based on acetylacetonate and phenylaminopentanone complexes of rhodium and optimization of conditions. And fourth goal was to study the characteristics of silicon rubbers obtained and the impact of catalysts on the mechanical characteristics, thermal characteristics, cross-linking rate, and luminescent characteristics if we use luminescent complexes. The cross-linking was conducted based on the following polysiloxanes. Vinyl-containing siloxanes included divinyl and dexavinyl polysiloxanes. As hydride-containing polysiloxanes, we used polymethyl hydrosiloxanes or a copolymer. For the cross-linking, we used two-component systems. The first component included catalysts and vinyl-containing polydimethyl siloxane. A second component was mixed. Then we used thermostat at a set temperature, and after a curing time, we got silicon rubber that was ready-made. And within the framework of the next field of study, we studied the catalysts that allow us to get luminescent silicon rubber. Phenylpyridine complexes of iridium-3 allowed us to carry out cross-linking at set temperatures starting with 125 degrees. Optimal temperature made up 150-180 degrees Celsius. Most active catalyst was the complex with one group. Less active complex was dimer complex of iridium-3. As these phenylpyridine iridium complexes are luminescent, it would be logical to say that silicon rubbers will be luminescent as well. And in fact, spectroscopy demonstrates that this post-luminescence is different from complexes luminescence, and we have a pronounced peak at 440 nanometers. And the difference from the luminescence of initial complexes can be explained by partial breakdown and transformation of complex during the curing. Phenylpyridine complexes of platinum-2 were also inactive in cross-linking reaction at room temperature. Yet, the optimal range was lower, 100 to 120 degrees. Chloride and triphenyl phosphate complexes are most active. When we replace one of the ligands, catalytic activity drops, as in case of platinum-1 when triphenyl phosphate ligand is replaced, and in case of platinum-4 where the replacement was done for chloride ligand. The introduction of two ligands, additional ligands, reduces the catalytic activity even more. The platinum-2 complex is least active. Phenylpyridine platinum complexes have strong luminescence. And above all, silicon rubbers obtained actively luminescent, and quantum yield reaches 12%, as in case of silicon rubber and platinum complex, when we use the complex with two isonyl groups of platinum-2. And microscopy of luminescence and confocal luminescence demonstrate that spherical particles and threads are responsible for luminescence. And mass spectrometry and extracts of silicon rubber demonstrates that luminescence happens due to initial catalyst. Thus, phenylpyridine complexes of iridium-3 and platinum-2 allows us to cure polysiloxanes at increased temperatures. Iridium complexes require higher temperatures, 150-80 degrees Celsius, compared to platinum complexes, 100-120. Obtained silicon rubbers have luminescence characteristics, and luminescence profile for phenylpyridine complexes combine is equal to the luminescence of silicon rubber and initial catalysts. A second field included the search for catalysts that would allow us to find an alternative to karsted catalyst. Nitrile complexes of platinum-2 allowed us to carry out curing in the concentration range that is given here. And they were applicable for cross-linking at room temperature and at heating up until 80 degrees. Most active was the complex with nitrile ligands, and cis complexes were most active compared to trans isomers. And depending on the catalyst, the concentration and temperature characteristics, we can vary the curing time from several minutes that can be used for dental molds to several hours. That is desired if we talk about modeling clay for children. And other studies demonstrated that nitrile complexes of platinum-2 improve the elastic characteristics of silicon rubbers. Such extension at rupture has increased up until 135% compared to karsted catalyst, and resistance is just the same. The strength is the same. And swelling experiments allowed us to state that the structure of the chain changes rather poorly compared to karsted catalyst. The mass of fragment between the cross-linking hubs made 9,600. That is comparable to karsted catalyst. Acetylacetonate and phenylaminopentanol complexes were considered as an alternative to karsted catalyst based on a different platinum metal, based on rhodium namely. And it turned out that these complexes allow us to have cross-linking at room temperature. And most active is the complex of rhodium-1 with the acetylacetonate ligand. And in concentration of 10 taken to the degree of -5, this time of curing was 116,000 seconds. So it allowed us to state that it improves the elastic characteristics, and the extension at rupture increases significantly. And the experiments on swelling demonstrate that the mass of fragment between the chains increases 2 times compared to karsted catalyst. Thus, nitrogen complexes of platinum-2 allows us to carry out cross-linking of polysiloxanes in hydrosylation in the temperature range from 20 to 80 degrees Celsius. Acetylacetonate and phenylaminopentanol complexes allow us to carry out cross-linking at room temperature, and nitrile platinum complexes and rhodium acetylacetonate complexes increase the extension at the rupture characteristics. And the conclusions of the work are given here on these 2 slides. Thank you, Mikhail. Just 2 more slides. Yes, okay. Within the framework of this work, I've published 4 articles in Web of Science and Scopus journals, and I got 2 patents as well. And in conclusion, I would like to thank the Institute of Chemistry employees, Professor Kukushkin of the Russian Academy of Sciences, then Associate Professor Kinzhalov for phenylpyridine, platinum, and iridium complexes, Professor Boyarsky, and Professor Rut for rhodium complexes. And I've I would like to thank Professor Vlasov for the conducted research on the method, and I would like to thank the Resource Center of St. Petersburg State University that allows us to organize meta measurements. Thank you. Thank you, Mikhail. Distinguished colleagues, distinguished members of the board, do you have any questions on the report? If you have some, we can ask questions on the work. So, Alexander, please, you have the floor. So, how long when did you contact Ruth? Did he bring Omicron here? No, it was long ago. So you're talking about dentistry and about child creativity. What about toxicity of all these complexes? Can they leak through silicone rubbers and harm people somehow? Well, above all, I should mention that silicone mixtures that cure with platinum metals, they are used in medical for medical assignments as well, so they are already used as implants, but toxicity should be minimal, that's it. And concentration here is at 10 taken to the degree of -4, -5 mol per liter, so these are rather safe materials, so to say. So did you conduct the study? No, but based on literature data, they are safe. They are rather safe. Okay, thank you. So, Mikhail? Thank you. Let us consider slide number 19. So, here you say that curing time on your rhodium complexes is minimal, 5 minutes, and a Karst's catalyst has a much longer time, and you say that that's one of the advantages of your system. And at that, on one of the first slides, when you mentioned Karst's catalyst, you said that it's most active, and in some cases you need to add up an inhibitor to reduce activity, and your complexes are even more active, as it turns out. So what's the connection here? The first thing to be mentioned is that at small concentration, the curing time is similar. 10 taken to the degree of -5, 60 minutes that were mentioned here, and for rhodium that's 72 minutes. And when you have this 160 minutes, I don't see it. I don't give this information here. That's 10 taken to the degree of -5 for Karst catalyst, 60 minutes over there. And for rhodium 1, that's a lower blue line, lilac line. So you can dissolve Karst a bit, and it won't be so active. You won't need inhibitor. How do you compare this result? How do you juxtapose them? How do they match? Do you need to find this high activity? High activity is it a does it act to the detriment, or is it an advantage, or what? If we talk about curing time, in this regard, the time of catalytic activity can be both an advantage and disadvantage depending on the application. And in this case, it's interesting that based on literature data, rhodium complexes are active at increased temperatures, at room temperature here. Okay, I have yet another question. Slide 17. You mentioned that cis complexes are more active than trans complexes. Yes. Do you have any explanation for that? Well, first I believe that's a steric effect, and then the impact of ligands. And Can you please add up some details about the impact of ligands? During hydrosylation, we need preliminary activation of the complex. And therefore, we need to detach one of the ligands. In this case, trans complexes are more stable than cis isomers. Okay, and the last question that I wanted to ask you is about luminescence. Judging by the spectra that you've given for the luminescence, all your silicon rubbers are luminescent regardless of the metal center in this narrow band. So we've shown it for iridium. And do you have such graphs for other characteristics? For other two, I don't give the graphs here. So I believe the range is similar. And why? Why so? Because the metals are different and luminescence should be in different bands. Well, for iridium, luminescence is nearly the same. Yes, okay, if you have iridium everywhere, that's it. So that's the breakdown and transformation of complex. And as for platinum and rhodium, they are luminescent as well. The platinum complexes, for them initial complexes stay in silicon rubber. It's proven already, and luminescence spectrum is just the same. And this can be seen from peak location and quantum results. And plus mass spectrometry experiment. We've taken silicon rubber, then concentrated the extract, and after that we used mass spectrometry. Okay. And at that, the most intensive peak was just the same for mass spectrometry of the initial complex and for the extracts. Okay, I got it. So the last question. As for the technology of acquisition, I did not catch it initially. So you mix two components from two syringes in the combination that you need. And does your catalyst dissolve that well in siloxane? Or is it a kind of suspension? Why don't you use the solvent here? I was surprised to see it. Well, that's a scheme, you know. Initially, the first component with vinyl group and catalyst, catalyst was initially dissolved, and dichloromethane, and after that it was administered. And then it was evaporated in vacuum, and it did not precipitate, basically not. Certainly it would be nice to see it on the scheme. Okay, thank you. Thank you, I have no more questions. Any other questions? Thanks. Yes, I would like to ask. So, the first question is technical. Why when we take cars and catalyst without inhibitor, we get poor quality rubber due to higher other thermal characteristics of the reaction? So why do we have these bubbles and uneven structure? Just a second. So the defect formation is due to the fact that that's preliminary reaction, and the mixture does not allow to scatter to spread across the surface. And when we mix that all, everything stays during curing. Okay. Okay, thank you. Another question, maybe more of a philosophy one. From some years I've been working with silicon chemistry, and I know that 7 years ago a lot of money was spent on stop using platinum complexes to start using cheaper complexes. And did you see some success of this undertaking in literature, the replacement of platinum group for cheaper alternatives? Yes, in literature there is an active search. We see an active search and a lot of publications on the topic, but the problem is some side reactions. For example, carbonyl complexes of ferrum can form, and they provide side reaction. You had dehydrating cellulation or something like that. So basically, the literature demonstrates that it's possible, but we don't have this good option currently, the best option currently. Okay, and the last question. Well, I see that there are limited catalyst range of 10 taken to the degree of -5. So does it influence characteristics, temporal characteristics? Maybe it increases the destruction or something like that. Did you conduct any studies? So how stable it is in time, a year, 2, 5 years? Well, silicon rubbers, based on the previous tests, they are quite stable and they do not change color. They stay transparent. And at that, based on literature sources, what we observed in our study, platinum complexes improve thermal stability. And during heating, we have this radical cross-linking. So platinum complexes improve the quality of silicon rubbers. Thank you. Thank you, Sergey. Nadezhda, you had a question. Yes. One question on slide 12. The concentration of complexes, you give 10 taken to the degree of -4 for luminescent materials. How do you define these characteristics, by catalytic activity or by the margin of luminescence? Mostly by catalytic activities. So they were easier to obtain. So luminescence at lower concentrations is possible. Yes, yes, that's it. And slide 14. Platinum 2 catalyst. That's a material with highest quantum yield, and that's least active complex. Did you try to coordinate it somehow, luminescence and activity? Maybe it's associated with the fact that this complex breaks down. Well, as for breakdown, I believe it can't explain, because for platinum 3 the quantum yield is nearly comparable, 0.9% and 1%. And for platinum 4 it's 4943. Therefore, I believe it's not breakdown. Okay, thank you. Thank you, Nadezhda. I have a question as well on slide 16. You see, here you position your product as potential material. Do you have any ideas about adhesion strength of combination silicon metal and abrasion resistance of your materials? Just maybe some ideas as for adhesion to metal. Silicons have a nuance that on the one hand they spread well, and in the initial state they are liquid before vulcanization, before the cross-linking, but they need some kind of chemical bond. Therefore, based on literature data, mostly if we apply silicone coating, we need to use primers that contain something that contracts hydroxyl groups of metals, and they have something that is comparable to silicone rubbers, mostly something that has a vinyl group. It's done when you need a chemical bond, the adhesion due to the use of chemical bond. And at that, you get a sandwich from metal, then primer, then different silanes with the toxic groups, and vinyl group, and then you have silicone rubber coating. And as for the resistance and strength to scratches and wearing off resistance, certainly they are less stable, silicone rubbers, compared to polyurethane materials. But on the other hand, there are several publications that show that thin layers of silicone rubber, for example monomolecular layers that are chemically attached to the substrate, they are rather stable. For example, in one of the articles they say that they could not scratch them with the razor. Thank you. Thank you. Do I get it right that these are literature data? Yes, mostly yes. And in this study, adhesion was not studied. Okay. Distinguished members of the board, any other questions on the report? Okay. As there are no other questions, I believe we could shift to the next part, to the speeches of the members of the board with their reviews on the thesis. I believe we can make it this way. We can read all the reviews, and after that the author answers all the questions, or we can answer all questions at once. For example, one review is read out, and after that we listen to the answers of the candidate for the degree, answer followed by a question followed by an answer, and if there are no objections, I believe we'll make it this way. And as all the reviews were already published on the St. Petersburg State University website, I believe there's no need to read out the review, just give us the key points and the comments about the work. No objections about that? Okay. Okay, then that's what we're going to do. So let's start. And I would like to give the floor to Nadezhda Bokoch first. Distinguished colleagues, the work is dedicated to the search of new catalysts in vulcanization of siloxane materials. And he studied 3 groups of complexes as catalysts for hydrosylation. And the work is really targeted to study how new catalysts impact the characteristics of polymers, and you study the regularities that connect the activities of the catalysts of hydrosylation to the composition and nature of the catalyst. And Mikhail mentions that there are a lot of catalysts for hydrosylation, but the majority of studies are associated with hydrosylation of relatively small molecules, and hydrosylation of polymers has its specificity. We know less catalysts and cursed catalysts, regardless of all the advantages that it has several drawbacks still. Therefore, it can't be seen as a universal one. Therefore, the search for new catalysts define novelty and relevance of the work. And above all, Mikhail offered an interesting idea to use luminescent complexes simultaneously as catalysts and as fillers for new materials. And this idea, I believe, can be developed further on. And I believe that there can be some practical application for that as well. And when I read the work, I had the following questions. I will read them out. On page 16, you mentioned that shell-carried mechanism does not explain the formation of vinyl silanes, unlike a modified mechanism. And on figure 3, you don't show how the second mechanism may lead to vinyl silanes. In section 1.1, you don't provide the hydrosylation schemes, and sometimes they lack. when you discuss catalysts. Then page 33, you say that the introduction of electron donor ligands reduces the activity of platinum catalysts of hydrosilylation. So I would like to solicit your explanation on that. And on pages 50 and 58, you say that catalysts of iridium-4 and iridium-5 are less active because two isocyanate ligands in the structure create steric hindrances for the implementation of the catalyst cycle. And you don't prove that these ligands stay in the content of complex as for platinum. And it's likely that they undergo certain transition that's demonstrated by the curing temperature and differences in the spectra of emissions for rubbers, and maybe this small activity is associated with less thermal stability. For example, bis-isocyanate complexes strongly break down for metallic iridium. Did you see the formation of metal after curing? Or maybe the formation of some other combinations. And on page 57, you show that less active catalyst iridium-5 provides for higher cross-linking of product. Could you please explain that? Because it's hard to understand it straight away. These remarks do not compromise the overall very high quality of the work. These are rather editorial comments. And I would like to mention that all the results of the work were published. 4 articles were published in journals, and 2 patents were obtained that demonstrate the high quality of the results. And I would like to read out the conclusion. The thesis by Mikhail Dobrynin, titled Complexes of Platinum Metals at Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers, meets the requirements of the order as of September 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University. And the candidate for the degree, Mr. Dobrynin, deserves the academic degree of Candidate of Sciences in Chemistry in Specialization 147, High Molecular Weight Compounds. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Nadezhda. Mikhail, please, you can answer. As for the first question, based on literature data, hydrating acylation can happen on one of the stages of the catalytic cycle, and at that, we see the Chuck-Harrod mechanism. So, after the attachment of silane to activated catalyst, we see the detachment of non-saturated silane, and then the catalyst hydrates another alkane molecules. And on this slide, you see the scheme that explains Chuck-Harrod mechanism and hydrating acylation mechanism. And you see that one of the stages, 2 stages are similar, and they are general. And as for the second question, based on literature data, we provide for one mechanism of hydrosilylation for all the catalysts, and therefore, in order to eliminate the duplication, I've given the scheme on page 16. As for third question, electrodonor ligands provide for the formation of stronger complexes with platinum based on literature data. That's Marcinic book. The difference of catalytic activity of platinum complexes can be associated with the speed of formation of catalyst complexes. And as for the fourth comment, judging by the change in the spectrum of luminescence during cross-linking, we have certain changes at heating up until 180 degrees Celsius. We see the yellowish color of silicon rubber when we use iridium catalysts, and this can be associated with metal formation during curing. Unfortunately, thermogravimetric studies of iridium phenylpyridine complexes were not conducted, therefore I can't confirm or refute this idea, this dependence on thermal stability of the complex. And as for the fifth question, on page 57, that's a misprint. Iridium-5 provides for a smaller cross-linking character rate for silicon rubber. And due to less catalytic activity of iridium-5, there are less vinyl and hydrate groups that manage to react, and therefore there's less cross-linking. Thank you, Mikhail. Nadezhda, are you satisfied with the answers? Yes? Yes, I am. I agree with everything. Okay, now I would like to give the floor to Alexander Yakimansky. So I like the work a lot. Basically, it's relevant, and that's due to the fact that silicon rubbers are quite in demand, both in technology and in medicine. And there are silicon rubbers with special characteristics, for example, luminescence. And why do you want to have this rubber luminescent? But still, these coatings are in demand as well in many fields. And here you add up optoelectronics with special requirements to materials, therefore. So these are all relevant ideas. The approach that was already mentioned by Nadezhda, when metal complexes being catalysts remain in polymer, providing for luminescence, is also an interesting one. Mostly we try to improve the qualities to touch something chemically, and these approaches were demonstrated by Mikhail at initial slides. But basically, that's a stage when rubber forms. And this approach is really quite interesting and, to my mind, promising. And as for the novelty, I believe all the results are quite novel. They were obtained for the first time, and the approaches are quite original, as it was already mentioned. Therefore, no problems about novelty, it's quite clear. And the practical value is clear as well. We need to develop new catalysts, because what we have some drawbacks, like the use of inhibitors, and such goals in the thesis are resolved. So there are different peculiarities associated with temperature conditions of processes, and that all is somehow managed. We optimize it somehow, and we elaborate a range of most optimal systems that combine high activities and high quality of obtained materials, and also in some cases they provide for high efficiency of luminescence as well. That is why we need to state that. And as for the remarks, the general one is as follows: why for complexes of metals and for rubbers he used different components. Those silicones. For example, for iridium complex, that's PDMS Vin 1 and HDMS for platinum Vin 2 and EHTMS, and for iridium that's Vin 3. So it would be logical to use the same substrate to assess further reactions wanted, because that's important considering my further remark. Because as for cross-linking efficiency, and for the plot between cross-linking hubs, For example, in conclusion to section 2.2, you mentioned that unlike silicon rubbers obtained using iridium phenylpyridine complexes based on VIN1 and EHDMS, when using platinum-2, we see higher rate of cross-linkings and reduced extension at rupture, and you say nothing about different substrates. And these initial components have different molecular mass. So these cross-linking terminals they are integrated in the formed mesh. Therefore, based on PDMS VIN2, you get less spin between the hubs. Is it associated with the characteristics of platinum, or maybe it's associated with the difference in molecular mass of the initial components and the length of the attachment to the mesh? Therefore, it would be nice if everything will be equal for all the complexes at the start. And as for platinum and rhodium, everything is okay from the point of view of luminescence, and as for iridium, it turns out to be quite low. It breaks down, not partially as it was mentioned in the report, but fully, I believe, because if it would break down partially, we would have some luminescence based on this initial complex. And considering the need for higher temperatures to work with this iridium, there's a question that arises of whether iridium complexes are the ones to be used to obtain such rubbers. So it would be nice to get a comment in the thesis for that, because it has a huge fundamental importance. These results have a high scientific relevance, but it would be nice to get some comment. That's not true for rhodium and for platinum complexes. That's okay from the point of view of practical application, from the point of view of temperature, from the point of view of inhibitor use. So basically, the goals are achieved here, and the remarks are more of a discussion, comments, so they don't compromise the overall high value of the work. And I would like to say that the thesis by Mikhail Dobrynin, titled Complexes of Platinum Metals as Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Dobrynin deserved the academic degree of Candidate of Sciences in Chemistry in Specialization 147, High Molecular Weight Compounds, and Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Alexander. So, Mikhail, please, you can answer. As for the question about different polysiloxanes, I agree that for correct comparison, it would be nice to take the same polysiloxanes, but for VIN1 and for VIN2, they are polysiloxanes with vinyl terminals, and there's no principal difference of what should be used for catalyst tests. Therefore, these results can be transferred to systems with other molecular masses. And the same is true for PMHS and EHDMS, and as for complexes and their breakdown time. Luminescence of silicon rubbers in the case described on page 53 is explained by decay products of phenylpyridine iridium complexes. Then we use platinum phenylpyridine complexes so that the luminescence would be provided by the complex itself. Phenylpyridine iridium catalyst should be used to obtain luminescent silicon rubbers regardless of the low efficiency of luminescence, because they will perform double function. They will be a catalyst of the reaction and luminescent filler at once, staying in the content of this polymerized product. Therefore, you don't need additional luminophores And in the work, we don't consider that the long-term goal is to study the electroluminescence of silicon rubbers. That is confirmed by publications of recent years in Material Chemistry Frontiers and in scientific reports, and as for the cross-linking in different polymers. During the curing of vinyl-terminated polydimethyl siloxane with a weight of 80,000 and hydride-containing polysiloxanes with a molecular weight of 8,150, with the help of complexes of radium 2, 3, and 5, we obtained MS that reached 5,400. And as for vinyl-terminated polydimethyl siloxanes with MW 80,000 and hydride-containing polysiloxanes of MW 8,150, during the curing for the reaction of catalyst hydrosylation, we got the result of 9,600. And cisplatinum 2 and rhodium 1 complexes demonstrated the change of MC values that are different, that are 2 times different. So thank you. Alexander, are you satisfied with the answers? Yes, I am. Okay, now I would like to give the floor to Mikhail Goichman. I would like to mention that in this thesis, we've seen a new method to obtain silicon rubbers using the new catalysts. And what's good and what's an advantage of the thesis is that the thesis shows the opportunities to use these polymers as luminescent materials and in other fields as well. And it should be mentioned that the development of state-of-the-art technologies require the development of new polymers that would be easy to, with characteristics easy to predict, but the opportunities to develop new polymers is limited due to the limited monomers. Therefore, the search for new promising compounds is of particular interest. And what else do I want to mention is that in order to develop these new materials, Mikhail used methods at which these materials are obtained in rather soft conditions, and that's, by the way, an important point from my point of view, because basically the cross-linking processes for polymers, and the majority of systems are cross-linked, they require harsh conditions, and this imposes certain limitations on the structure of polymers, and here those difficulties are something that the author managed to overcome. And as any work, this one has certain drawbacks, and as a comment I would like to mention the following one. During consideration of the medicine spectrum for iridium complexes, iridium 2, 3, and 5, that's page 54, the author mentions that in every case in spectra we have 2 peaks. However, he compares these results not with literature data about these complexes, but with literature data about other complexes, radium 4 and 6. Second point is that out of the presented results on page 56, it's hard to see what's the association of this difference in thermal stability of silicon rubbers, taking into account the fact that when we use different catalysts, terminal structures of cross-linked polymers are no different. And I'll explain here. I'm referring to the difference of structure. And on page 57, the author mentions that silicon rubbers with less active iridium 5 complex have a lower dissolved fraction, 2.7%, that demonstrates higher cross-linking rate. And on the next page, 58, the author mentions that average molecular mass of segment between the cross-linking hubs for iridium-2 made up 14,000 grams per mole, and for iridium-5, 18,000 grams per mole. And this demonstrates a lower degree of cross-linking for iridium-5, so the author should explain this contradiction. And it should be mentioned that these remarks are some general remarks, and they do not compromise the overall pretty high quality of the work. And the work has elements of scientific novelty. The conclusions respond to the targets set, and based on the above-mentioned remarks, I'm sure to say that the thesis by Mikhail Dobrynin, titled Complexes of Platinum Metals at Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers, meets the requirements of the orders of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Dobrynin deserves the academic degree of Candidate of Sciences in Chemistry in Specialization 147, Micromolecular Compounds, and Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Mikhail. So, Mikhail, you can answer. As for the first question, complexes iridium-2, 3, and 5 were for the first time synthesized by the team of Mikhail Kanchalov, and we have literature data for them only in publications that were made on this work. Therefore, we compared the situation with complexes 4 and 6 that are similar in structure. As for the second question about thermal stability, a difference in thermal stability of silicon rubbers is associated with the impact of silicon complexes on the mechanism of thermal destruction. And according to the literature data for platinum complexes, simultaneously with thermal destruction, we have a catalytic cross-linking of polysiloxane chains that increases thermal stability, and there are patents that use iridium complexes to enhance stability. For example, Gershow patent as of the year 2006. And thus, the difference of thermal stability of silicon rubbers are explained by the metal center nature. Now, the third comment. There's a mistake on this page. On swallowing experience, we can make a conclusion that when we use iridium-5, we obtained silicon rubber with higher MC and with lower cross-linking rate for iridium-2 and 3. And we base our conclusions on Valerievich equation. So, for the first question, yes, I agree with you. There are limited data in literature. As for the third remark, that was a mistake. And I would like to explain the second point. Thermal stability of polymers. So a thermostability index, so 0, 5, 10, loss percentage, and so on. So they are clear. I was talking about coke residue, and in the report you did not give this remarks, but I've seen them in the thesis. And the question is as follows, basically. Polymers that you study, they are a bit different in their behavior from other polymers. For example, carbon-containing polymers. Because when we have air presence and you perform test studies, all the carbon turns into carbon dioxide, and there's nothing in the coke residue. And it's quite the opposite for polysiloxanes. The presence of air gives us CO2 and the residue in coke residue, and when we have no oxygen, there are silanes that form, and we have volatile products as a result. For the first group of complexes, iridium complexes, everything is okay. When there's no air, the coke residue gives us some percentage, And in the presence, we have some 50-something%. And for the third group of complexes, for rhodium, it's unclear in both cases. You have a coke residue that is just the same whether you have air or not. That's what I meant when I asked this question. Can you explain that? So maybe that's a binding of carbon during the breakdown. And on the other hand, yes, it looks as an anomaly, because mass is just the same with air and without it in an inert atmosphere. And why so? Well, I see that that's experimental data and it's hard to dispute that, but maybe you have some explanation. Maybe we can presume that during the tests in argon, the air still remains in the polymer. Oh, and maybe it is taken into account in the residual mass. All that is possible if polymers are porous, then it's possible. Why not? Thank you. Thank you. Now I would like to give the floor to Sergei Kostyuk. Yes, distinguished colleagues, I would like to say that, to my mind, I liked the work a lot because I'm dealing with polymer chemistry myself, and this synthesis work in our age of material science is something that we like a lot. And basically, the goals were quite good. On the one hand, let's search for new catalysts for the curing of silicone rubbers. It's clear why we need that, because the candidate for the degree substantiated that in his work, that classical karsted catalyst has certain drawbacks. They need to introduce inhibitors that can be more toxic by several orders compared to the catalyst, platinum catalyst itself. And yet another comment, the original idea in this thesis is to design catalysts in a way so that we could add up a luminescent ligand so that the catalyst later on that stays in the polymer would have this photoluminescence for silicone rubbers. So that's quite unusual an approach if we talk about the expansion of this sphere of use for silicone rubbers. And indeed the work is written quite well, and there is a broad spectrum of physics and chemistry methods that was applied, and it characterizes the work quite well, that the author did not just devise catalysts and study their activities, but also got real rubbers, studied their mechanic characteristics, and for some, the author demonstrated luminescence as well. So to my mind, that's quite a good finished study. And the results were also published in 4 articles in high-ranking journals. There are 2 patents of the Russian Federation, and it emphasizes the practical value of this work. So we see that the author will continue the development of these ideas, maybe acquire specific materials for specific goals. And as a comment, I would like to mention the following one. So that's rather a wish than a comment. It would be nice to add up a short section, summarizing section, that would compare the activity and the efficiency of the developed catalysts, just to summarize it all and to demonstrate What are most efficient catalysts on offer from the point of view of the author? So I believe it would be nice to have such a section. Yet another question that I want to read out. What is the association between the reduction of lifetime of luminescence complexes of iridium and silicon rubber compared to the solution of CH2 chlorine 2? And another question is more of a recommendation. It would be nice to study as with iridium and platinum, we have increased temperatures. It would be nice to study the thermal stability of complexes before the curing. Another question is associated with the following fact. On page 67, you show that the luminescence of silicon rubbers happened due to spherulites and needle complex, crystalline complexes. But if that's a misprint because complexes won't form spherulites, and the last remark is that in the work you provide strength characteristics for volcanizates, the initial data. And in the text, I believe it would be nice to see the specific curves of deformation, strain for silicon rubbers, compared to, for example, silicon rubbers obtained using karsted catalyst. But these remarks rather are more of recommendations. They don't influence the assessment of this work, and I would like to state that the thesis by Mikhail Dobrynin, titled Complexes of Platinum Metals at Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Dobrynin deserves the academic degree of Candidate of Sciences in Chemistry and Specialization, Macromolecular Compounds, and Articles 9 and 11 of the above-mentioned order are not violated. That's it, what I wanted to say. Thank you. Thank you, Sergei. Mikhail, please, you have the floor. As for the first question about the comparison of catalytic activities, I agree with the remark. This section was not introduced, but I have data in the summary. But actually, I can say that phenolpyridine iridium complexes allow us to carry out the curing at temperatures 125-180 degrees Celsius. Phenolpyridine platinum complexes require softer heating, 120 20 degrees. And nitrile platinum complexes allow us to use room temperature and heating up until 80 degrees. I believe I believe the connection failed. Okay, I continue. Yes, it's okay now. Rhodium catalysts allow us to carry out the curing at temperatures 20-25 degrees. So depending on metal center and ligand surroundings, catalysts allow us to cure polysiloxanes using the hydrosylation reaction. And phenolpyridine platinum and iridium complexes allow us to obtain luminescent silicon rubbers. And for iridium complexes, luminescence is explained by products of decay of the catalyst, and platinum complexes by threads and spheric particles of the catalyst. And it also allows us to use to improve the elastic characteristics. As for the second question on the lifetime luminescence complexes, during the curing, we have a transformation that includes the change of ligand environment, and as a result, we see the change in the spectra of luminescence and the lifetime of silicon rubber compared to the initial phenolpyridine iridium complexes. Third question was about thermal stability of the complexes based on literature data. That's article of Wang. in Basel. Phenylpyridine, iridium, and platinum complexes give us the temperature of start-off decay at 200 degrees Celsius. Then, as for the fourth remark and fifth remark, as for the fourth remark, this was a misprint, and as for the fifth remark, mechanical curves. I agree with this remark. I have dynamic curves. I should have included them into the thesis, and on this slide, you see the examples of these curves. Sergei, are you satisfied with the answers? Yes, I am. Thank you. Thus, I believe it's my turn to read out my review. Well, initially I would like to say that we see the rise in silicone development. These materials are everywhere, though several decades ago they seemed to be quite exotic. And to add up a bit of philosophy in our post-industrial civilization, today, when we see this transition from mass production to the production of personalized items, the development of new materials, and in this particular case, new catalysts for the production of new silicone rubbers, so they are quite important. New catalysts are needed, regardless of the fact that currently we have access to karsted catalysts that are quite cost efficient. If I believe that that part of work that is associated with the study of new catalysts is certainly of paramount importance. And there are no questions regarding the need to perform this work. The second part of the work about luminescent silicones. So this can be a bit funny, and we do not discuss practical value right now, but I would like to draw your attention to the fact that this part of work is a private case of a generalized scientific problem of a generalized field of cost-efficient chemistry. And that's a discovery of the author, that you can use a catalyst, one of the components of the system, to give rise to other characteristics. And in this particular case, we are talking about luminescence, but the idea is that we can use minimal amount of components and get maximum yield, thus minimizing the content, the chemistry, to obtain quite accessible and functional characteristics for materials. And in this regard, the work has this academic value because it develops the principles of cost-efficient chemistry and cost-efficient material production with a minimal number of components. So it was very interesting to read this part of work as well. As for the thesis itself, as the text, to my mind, I believe the text is a bit laconic, too laconic. There are a lot of interesting results, a lot of interesting data, and during reading I lacked some explanation of these facts. I lacked scientific discussion, based on the facts. Certainly when it's written briefly and precisely, that's great. It's easy to read. But sometimes you just want to see a bit more discussion. You need to trace the logic of this academic thought of the author. And in my written review, I had 2 questions, and I need to read them out. Question number 1 is as follows. You mentioned that nitrile ligands have the opposite influence on catalytic activities of iridium and platinum complexes. Why so? A second question. What's the input of catalysts based on metals of platinum group into the cost of the end product? Is it the cost of new catalysts comparable to the cost of cursed catalyst? And finalizing, I want to say that the thesis by Mikhail Dobrynin, titled Complexes of Platinum Metals as Cross-Linking Catalysts and Luminescent Polysiloxanes Fillers, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Dobrynin deserves the academic degree of Candidate of Sciences in Chemistry in Specialization 147, High Molecular Weight Compounds, and Articles 9 and 11 of the above-mentioned order are not violated. So, Mikhail, you can answer. As for the first question on nitrile ligands, in this work, nitrile ligands are represented by platinum 5 and 8. And for phenylpyridine complexes, that's platinum 1 to 4, and they reduce activity, show reduced activities. And as for the catalyst cost, catalysts are used in small concentrations, 10 taken to the degree of -3, -5 mole per liter. And when we calculate the cost of components for curing mixture, if we are based on the price ranges of Merck, ABCR, polysiloxanes account for 99% of cost. So we should have the cost at the level of the cost of our cursed catalyst, but it's hard to think about the cost because the complexes were synthesized in small scale, and certainly this cost will change when we synthesize them in large scale. So, distinguished members of the board, are you all satisfied with the answers of the author of the thesis? Okay. As they are, as you are, I would like to ask the guests if there are any questions on the thesis. No questions from our audience. So I have a question on about some comments submitted via website. No comments from the website. On our website. So let us proceed. Now I would like to give the floor to the thesis supervisor, Regina Islamova. Thank you so much, distinguished chairman, distinguished members of the board, dear colleagues. Mikhail has been my student for 7 years already. He's not just my colleague, he is my associate as well. We started working on polysiloxanes together, and for these years we did much more than we included in the thesis. Misha synthesized interesting hybrids, and currently I'm pretty sure that Mikhail is an established young scientist, an independent scientist who is capable to work by himself, and currently he has over 10 publications, and the most recent one is with an impact factor of 9 something. He has 2 grants from Russian Foundation for Basic Research. He also got additional grants, therefore he spent these 7 years not in vain. He worked a lot, he did a lot, and I am sure that that's just the start for him. And characterizing the student as a talented one, as an interesting one, interested one, I can say that I really like to work with Mikhail because he's really a thoughtful person, a calm person, and really a brilliant colleague. Therefore, distinguished colleagues, I ask you to support his thesis and his candidacy. Thank you very much, Regina. Distinguished colleagues, distinguished members of the board, distinguished participants, does anyone want to say something? No one. Okay, let me just say a few words then. I had an opportunity to see the work of Mikhail and his study at the Institute of Chemistry, and I need to say that for these 7 years, Mikhail really grew a lot in his academic development. And I believe it's true that indeed he is mature enough to get the degree that he asks for, because this was quite obvious a growth. And I was pleased to see it within this year, so that's just a view from the outside. Because Regina, for example, saw this progress from the inside, and I've seen it from the outside. Indeed, this progress is quite pronounced. That's it. So, dear colleagues, does anyone want to add up anything? Yes, I want to say that I liked the work a lot. When I read it, when I heard the presentation, I would like to say that it's quite a fascinating work. And the advantages were mentioned quite by everyone. So the work has all the components that it should have. And second, the obtained results are significant. There's a scientific novelty in the work that should be respected as well. And what else do I want to say is that we need to assess not just the work, but also the candidate for the degree, because Mikhail had a very serious task. He should have showed that he has profound knowledge and skills in different fields of chemistry, in polymer chemistry, high molecular compounds chemistry, organic synthesis, chemistry of coordination compounds. So he demonstrated all his skills and demonstrated a good analysis of chemical dependencies during interpretation. That all allowed him to compile a fascinating and logical work, and certainly I will support this work. Thank you, Mikhail. So let us draw the conclusions then. Let's believe that here we stop the discussions and stop taking questions from the audience. And before we draw conclusions and vote, I need to ask the question to the members of the board and to the candidate for the degree if there are any remarks or questions about the procedure of our session, maybe the ones associated with the remote access. No questions? Nadezhda? No questions? Mikhail Yakovlevich? No questions? Alexander? No questions? Okay, thank you. Unless there are no questions, let us proceed. So, dear colleagues, before the vote, we have an opportunity to declare a 5-minute break to discuss the results of the defense, and this discussion will not be broadcast. So, how do you think, do we need such a break to discuss the results? Okay, no need for the break, therefore let us proceed to the vote. At that, I need to solicit your opinions public, and you need to voice them publicly. So it's 16 minutes to 1, and we start the vote. So we all see each other, hear each other, the broadcast is on. And therefore, I raise a question on the award of the academic degree of candidate of sciences in chemistry in specialization 147, macromolecular compounds, to Mikhail Dobrynin. And I would like to emphasize that voting for the award of the academic degree, each member of the board agrees that the Article 11 of the order is not violated by the candidate, and let me quote it. Article 11 in the thesis, the applicant for the academic degree is obliged to cite the author and or the source of the materials or individual results borrowed, using the results obtained by the applicant personally or in co-authorship. The applicant for the degree is obliged to know the circumstance in the results. And let me remind you that the decision of the dissertation board on the conferring the academic degree is positive, provided more than 50% of the board members, but not fewer than 3 people voted in favor. That's in conformity with section 23 of the order. So, Nadezhda Bokach, what's your opinion? I will vote for the award of the academic degree, because the work fully corresponds to all the requirements. Okay. Alexander Yakimansky. I also vote for the award of the academic degree, and I believe that the work should get this degree. Okay, Mikhail Goichman. I also vote for. I believe the work corresponds with all the requirements, and the author should get the degree. Okay, Sergei Kostyuk. Certainly I will vote for the award of the academic degree, and I believe that the work corresponds with the requirements for the PhD thesis. And I, chairman of the board, Ivan Zorin, vote for the award of the academic degree to Mikhail Dobrynin. Thus, distinguished colleagues and guests, I would like to announce that out of the 5 board members, 5 voted for the award of the academic degree, no 1 voted against, and no 1 abstained from the vote. Therefore, we award the academic degree of the candidate of sciences in chemistry in specialization 147, macromolecular compounds, to Mikhail Dobrynin. And now I would like to give the floor to Mikhail for the finalizing remarks. First of all, I would like to thank the board members for the opportunity to deliver my report. I would like to thank the chairman of the board, Ivan Zorin, and all the members of the board, Sergei Kostyuk, Nadezhda Bokach, Alexander Yakimansky, and Mikhail Goichman, for their attention and for valuable remarks. And I would like to thank Regina Islamova particularly for her supervision that started during my bachelor course and still continues. And I would like to thank Professor Kukushkin for his help and recommendations. And I would like to thank Associate Professor Kinzhalov, Professor Boyarsky, and Professor Rud for complexes of platinum metals. And I'm sincerely thankful to Resource Center of St. Petersburg State University. And I would like to thank other colleagues who provided rubber materials to me. I would like to thank Konstantin Ziryabin and all the guys in our academic group for their support. Thank you all. Mikhail, we congratulate you sincerely on the award of the academic degree of Candidate of Sciences in Chemistry. Dear colleagues, that's it. I therefore end our session, and I ask to turn off the broadcast. Thank you.